explained a little bit on continuity equation at the first part of this lecture. Okay. So this is the derivation of continuity equation. Okay. What we do is we want to analyze what happened at the center of the cube. So whatever goes into the cube and out from the cube, so this is the component. For example, this is the x component. This one is y component. This one is z component, right? And how we calculate this one is we're gonna minus out the component out from the system with the component into the system, become 0. Okay, so what happen is rho u plus del rho u over del x. Okay, del x divided by 2, del y and del z. Okay, this is the outflow component minus the inflow component, rho u minus del rho u del x, and then del x divided by 2, and then you have del y and del z, right? So rho u minus rho u, you're going to cancel out. So this term, since you have a half of it, so negative become positive. So in the end, what you have is del rho u over del x. So half become del x, del y, and del z. Okay. So this is the x component. So similarly, occurs or calculated for y component. So in the end, what you're gonna have is del rho v over del y, del x, del y, and del z. Okay. And similarly, it's gonna happen with the w component, del rho w over del z, right? Del z, right? Okay. And then del x, del y, and del z. So in the end, continuity equation, since we minus out outflow minus inflow, both are the same. So all of it becomes 0. So your equation later becomes something like this. Del rho u over del x plus del rho v over del y, and then del rho w over del z. Okay. Del x, del y, and del z equals to 0. So yeah, mathematically we can cancel out this one, right? Meaning kita transfer ke sini lah, jadi kosong. So your continuity equation become this equation. Okay, right. But remember, every term must have 4 dimension. Not 4 dimension lah kan, 3 plus 1. So time. Okay, del rho over del t plus del rho u over del x plus del rho v over del y plus del rho w over del z. So this is continuity equation in general form. Okay. Any question? Okay. If no, I continue. Right. All right. So this general equation is actually valid for compressible and unsteady. Okay, if you have a problem which is compressible, let's say for chapter number 5 later, and the specification or parameters of those system is changing with time, so we consider that as unsteady flow. Okay, so we want to apply this equation. But for example, let's use those example just now. Two piping system, one small, one larger, and the velocity at A, VA is 2 meter per second, and at B, so since this is larger, perhaps it's become slower, 4 meter per second, right? Okay, hear me out. The important thing is, the important term is, first, this is a piping flow, fluid flow inside a pipe. So commonly, it's not going to be compressible flow. It's going to be incompressible flow. Why? Tak logik lah kan? Dia flow dalam pipe boleh menjadi until a certain Mach number. Okay, tolong calculate, tolong cari kat saya guna Google. What is the velocity of Mach number? Anyone? Mach number 1 for example. Berapa value dia in terms of meter per second?
.343.2 meter per second.
Alright, 343.2 meter per second. Laju ke slow?
Laju. Sangat.
Sangat laju kan? Satu saat. Saat kedua, 343 meter per second. So nonsensical untuk piping system. Right? So now, this problem is incompressible. So incompressible meaning density, meaning, ini bukan incompressible rule. No, meaning bermaksud density constant. Jangan salah faham macam senior you all. Dia ingat density kosong. Habis dia cancel out semua equation. No, constant. So like what we do with this one, del x, del y, del z, because this one is equals to 0, constant kan? So we can basically, benda yang sama, 10, 10, 10, 10 density, we can put it the other side. So meaning we can cancel out the row. So your equation now become del u over del x plus del v over del y plus del w over del z equals to 0. Any question? Okay, if no, I continue. So I already explained to you this is valid for incompressible flow, and this is also valid for steady flow. Okay, so what it means by steady flow, notice this one. Okay, normally in your exam question, soalan dia tak berubah kan? Dia hanya bagi tahu 2 meter per second, and then they told you 4 meter per second. Ada tak? Is there any question that after a certain time, katalah selepas 20 saat, yang ni berubah jadi 6 meter per second? Pernah jumpa? Pernah tak jumpa? 4 meter, tak ada kan? 4 meter per second pukul 8 pagi. And then VB change 6 meter per second pukul 9 pagi. Analyze. So if you have this case, it is actually unsteady. If it is unsteady, salah lah ni. You cannot use this equation. You need to put the time. Okay, this time. So no, none whatsoever, tak pernah jumpa. But in real world, ialah ada. Okay. So this is valid for steady flow. So the keyword is at any given time, the velocity at A 2 meter per second, the velocity at B 4 meter per second. At any given time. 2 petang, 3 petang, 5 petang, besok, tomorrow, dia tak berubah. Okay. So steady flow. Okay. So this is the continuity equation for steady flow. And I can say you can use this one for chapter 1 until chapter number 4. Okay. Kan? Tak ada, saya rasa tak mungkin. Right? Because always incompressible flow. Alright, any question? Okay, if no, let's do this one. Okay, this is a final exam question. Can't remember which year. Problem 1.4. The velocity components of an incompressible flow field are suggested by the equations u equals to 2xy, v equals to negative x to the power of 2 multiplied with y, and w equals to 0. And they ask you to show that the flow is impossible. Okay, so we can check through continuity equation, right? So the first rules they give you is actually incompressible flow, meaning you cannot use this equation. You have to use the one at the bottom. Okay. So del over del x, u berapa? 2xy. 2xy plus del v over del y. So del over del y negative x squared y plus del over del z. Kosong kan? So this one equals to 0. Alright, so what is the value for 2xy differentiate to x become? Berapa ni?
2y.
2y plus berapa?
Negative x square.
Negative x squared equals to 0. So is it impossible or possible? Impossible, right? Because suppose this term, if possible, must also 0, equals to 0. So since this one is not equals to 0, the flow is impossible. Does not follow the rules of continuity equation. Okay. Any question? If you found 0 equals to 0, then the flow is possible. Then the flow is sensical. Okay. If not, the flow is impossible, meaning something wrong with the governing equation. I mean, the component equation. Something is wrong. Okay. All right. Done. So that is chapter 1.2. Continuity equation. You're going to use this a lot later in Navier-Stokes equation as well. Any question?
No.
Okay.
No, sir.
All right. So recap back. So you have chapter 1.1. What you've learned on chapter 1.1?
Local acceleration, convective acceleration.
Yes. Local acceleration, convective acceleration, velocity field, correct? Even though the equation that I gave you is acceleration field, but inside the acceleration field, you have velocity field, del u over del x, del u over del y, remember? Okay, those are the velocity field. Chapter number 2 is chapter 1.2 is continuity equation. All right. So next we go to the next subchapter. Subchapter 1.3. Okay. So this is the Navier-Stokes equation. Page number 16. If you haven't downloaded, you can download from Google Classroom. Okay, if you notice, the first part would be the continuity equation. Okay, this one is continuity equation. Sorry, the first part would be the acceleration field. Okay, del u over del t, rho u du over del x, v du over del z, and w du over del y, w du over del z. Okay, this is acceleration field. And you have this one is pressure difference, and next is the shear stresses. Remember tau. Okay, mu du over dy, but this one is actually first order. This one is second order, meaning we multiply it further twice. Why? Because of derivation. Okay, but the thing is, the component itself is valid for shear stresses. So this is shear. Okay, and the last part will be the gravitational effect. Okay, so those are the component for Navier-Stokes equation. For Cartesian coordinates, for x component, y component, and z component. Okay. So next, I introduce to you Navier-Stokes equation as well for the cylindrical coordinates. So instead of x, y, and z, you have r theta direction, meaning in this direction, and then z. Okay, r, theta, and z. So you have a radial component, tangential component, axial component, which is the z. Okay, so the same equation but different mathematical symbols or mathematical equation. Meaning, this one also representing shear, this one also representing gravitational, pressure difference, and acceleration field. Okay, the only difference is RZ and theta for the axis. Okay, all right. So your assignment. I'm going to give you assignment. Derive Navier-Stokes equation for Cartesian coordinates. Okay. Yeah, derive this x component, y component, and z component. So how to derive this one? You're gonna use the same concept with this, which is we call this as finite volume method. Okay, finite volume method and differential approach. Okay. So you can find from books or anywhere, discuss with your friend and all. So in the end, your answer will be this equation. Okay, submit bila tu? Saya tanya Nur Izwani, bila awak nak submit? Terkejut yang lain.
Next week.
Itulah
Saya
terkejut.
tanya Nur, saya tanya Nur Izwani. Okay, Nur Izwani, bila? Rajin Nur Izwani ni, mandi dia hantar. Kita hantar hari Khamis lah Boleh Nur Izwani? So next class, this class on Thursday, before class, not after class. Boleh? Okay,
Boleh,
so
boleh.
I will open up GC for you to submit. Maybe you can submit to GC lah, Google Classroom, right? Right. Thank you, Nur Izwani. Okay. So continue. Okay, even though we have 10 minutes, but still 10 minutes is a lot of time. Okay. But we use this differential equation. Okay, we use that to solve commonly flow between two plates. Okay, if you have a fixed plate, okay, at the bottom is fixed plate. Normally, when you have a plate, this black color line is actually a plate, and if you have lorekan bawah tu, meaning it's actually fixed plate. And you have at the top is actually a moving plate. There is a special term for it. We call this as quake flow. Okay. Do not afraid. I mean, yalah, nama saja, just a name. So you know quake flow is actually one fixed, one moving plate. Alright. So I told you just now commonly known fluid problem where saya bagi contoh. Okay, for example, you have a conveyor. Kan? You orang selalu beli barang kat Shopee betul? Shopee ke Lazada?
Shopee.
Shopee.
Alright. So you have a conveyor which is to transfer goods. Any goods lah. You beli iPhone 5 kan? iPhone 10 ke? iPhone X. Okay, this is the... Saya tambah je. Tak ada kaitan pun ni. Ni tempat barang tu nak masuk later, and then after that kat sini ada JNT kat sini. Ambil barang tu. Hantar kat IBA. So this is conveyor. So it move from left to right. So this conveyor maybe not a flat plate, but we can consider that as a plate because keras lah kan. Okay, takkan lembut. So this conveyor must be on top of something. So in between, perhaps, this is an example kan, perhaps in between there is a fluid layer. So bottom is fixed plate, top is actually moving plate. So this is the case, right? So what is the next example? Okay, so I'm not gonna try to calculate this because we don't have time much. So I just give you example of the other problems that you're gonna encounter during your final exam or everyday life. So next is piston. You know piston? Siapa tak kenal piston? Ada yang kenal?
Kenal.
What is the purpose of piston?
Kenal.
Yang ni kita panggil apa?
Rod.
Boleh, ada lagi nama dia. Connecting rod. Kan? Yang ni kita panggil apa? Crankshaft or camshaft?
Camshaft.
Cam or crank?
Cam.
Crank.
Crank. Saya nak tanya seorang. Hana Rafifah. Crankshaft or camshaft? Yang saya tunjuk tu. Yang bawah bulat.
Crank kot tak tahu, tak sure.
Okay, very good. Yeah, crankshaft. Pandai. So this is actually crankshaft. Camshaft yang kat atas the one that we want to put a mix of oil and air into the piston chamber. Chamber piston chamber. Okay, piston chamber. And the one that after exhaust, after explosion, and want to exhaust out from the system. So this is crankshaft. So all of these are besi kan? So in between, you're gonna have what? Apa perlu ada kat sini?
Minyak.
Minyak. Very good. Is it minyak hitam? Kan? So this is actually a fluid, right? So the same concept, you're gonna apply plate with a fixed dinding. Now it move, perhaps in that instance, kita analyze yang moving outward saja. So same with this one. But the problem is, it's not a problem. But the thing is, maybe the axis. Now the axis, this one is Y, and this one is perhaps X, for example. Right? So this is another example. Okay. So next is, you still have 4 minutes. Next is this one. Flow between two plates. When you have two fixed plates. You have this one, and you have another one. And this one you have what we call as a velocity profile. Velocity profile, some question, they give you the drawing of it, but some does not. But you need to be able to determine what kind of velocity profile occurs inside this plate. For example, since you have two fixed plates, top and bottom, and there is a flow from left to right. So how the velocity profile looks like? Or sensically, or what can I call it? Logically, okay, should be fixed. So the one that near to the plate is gonna be 0, right? And due to roughness of surface and the shear stresses among the fluid, this is fluid. Line number 1, line number 2, line number 3, and line number 4. All of this line is actually fluid, represent fluid. But from fluid 1 compared to fluid 2, there is still a shear stresses. In between fluid also ada shear stress, meaning friction. Okay, so that's why you have in the middle maximum velocity. But towards the fixed plate, it's going to be reduced. Okay. This arrow does not saja-saja. This arrow meaning the longer the arrow, meaning the higher the velocity. Okay, it's not saja-saja lukis, right? Okay. So how does the velocity, the fluid flow from A to B? Anyone? How can fluid flow from A to B? Because of what? What is the influence of it?
Pressure.
Very good. Siapa tu? Tak sempat tengok nama. Siapa?
Aeroequan.
Aeroequan. Very good, Aeroequan. Due to pressure difference. Kan? Imagine if pressure A equals to pressure B. Can the fluid flow?
No.
No, because belakang 10, depan pun 10. Memang tak berjalan lah flow dalam tu, betul? So, when there is this kind of flow, you should know as an engineer. Later you dah jadi engineer senior, lagi lah tahu. Okay, meaning PB larger or lower than A. Pressure B
Lower.
should be lower. Yeah. Pressure B should be lower than pressure A. So then there will be a flow from A to B. Okay. So this is another common problem. Okay, so yeah, that's all for today. Any question before we end our class? Ada soalan? Semua faham?
InsyaAllah faham sir.
Alright. Very good. Okay. So this is 7B. Wait. So I put it in the chat box, your attendance sheet. Okay. Boleh tolong isi sekarang? Oh, sekejap. Salah. Betul lah. Betul. Sorry.